Welcome back to this course on fundamentals of computer architecture. In this lesson I will present some examples that illustrate how Amdahl's law can be applied. Here are two examples of applications of Amdahl's law. Because Amdahl's law is a simple equation with a few unknowns, many questions based on it can be asked. First, the newly hired young architecture has improved the floating point unit of our new processor so that all floating point instructions run twice as fast. Everybody is really excited about this breakthrough, and the party is about to begin when somebody enters the room and says, "Yes, but in the benchmark set we target only 10% of all executed instructions are floating point instructions. What will be the overall speed up then?" Somebody else in the back of the room once attended a lecture about Amdahl's law and answers, "I can calculate that." He writes down on the whiteboard, the overall speed up S equals 1 divided by the fraction that is not improved, 1 minus small f, plus the fraction that is improved, small f, divided by the factor of improvement, big F. This equals 1 divided by 10% is improved, so 90% is not improved. So 0.9 plus 10% is improved divided by 2, the factor of improvement. Then he enters these numbers into his calculator to find the overall speed up is approximately 1.0353, roughly 5%. This is still a very good achievement, and it will be a tremendous job if all floating point instructions are accelerated by 2x, but the company will probably not make a lot of extra sales thanks to this 5% improvement. Here's the second application of Amdahl's law. We want to achieve an overall speed up of 2 and can accelerate floating point instructions by a factor of 4. Now the question is, what should be the fraction of floating point instruction so that this overall speed up of 2 is achieved? Here's the answer. This time I will not explain it in detail to you, assuming that you have now sufficient information to solve this question by yourself. Amdahl's law is a simple equation, but it has some important consequences that you should be aware of. To illustrate these implications, let's look at this figure representing the execution time of an application consisting of two independent parts, A and B, since we found no better names, where the red part A takes about 4 times as much time as the blue part B. Now we make the blue part B 5 times faster. Then the execution time will look like this. The blue part B has become very small, but the biggest red part is still there. Alternatively, we can make the red part A 2 times faster. Then the execution time will look like this. The red part A has become smaller and the smaller blue part B is unchanged, but the overall improvement is larger than when B is made 5 times faster. What is the moral of this example? This example teaches us the following rules of thumb. First, we should focus on the common case. We should make the common case fast. It doesn't help us if we improve only 1% by a large factor of, say, 100. It makes more sense to improve, let's say, 50% by a small factor of only 2. This example also illustrates the so-called law of diminishing returns. The more you optimize a certain part, the less effect it will have on the overall execution time, unfortunately. I conclude this lesson with some other rules of thumb that can be exploited to make processes faster. First, take advantage of parallelism. Parallelism can be exploited in different ways by using pipelining, instruction level parallelism or ILP, data level parallelism or DLP, and thread level parallelism or TLP. We will see all these different levels of parallelism and how they can be exploited in the lessons to come. The second rule of thumb is the so-called principle of locality. Locality has many forms. One is locality in time. For example, another rule of thumb states that programs spend about 90% of their execution time in only approximately 10% of their code. So it makes sense to focus on this part of the code. Another form of locality is locality in space. We can predict with very good accuracy the instructions and data the program will use in the near future. On this form of locality, caches and the memory hierarchy are based. Third, and finally, and which is related to the previous one, make the common case fast, as is implied by Amdahl's law. Since this lesson is the last one in a series of lessons on performance, it is time for a short summary. First, there are many aspects of computer performance. For example, latency, the time from the beginning to the end to get a job done. Throughput, how many jobs can be executed per time unit. Availability, the fraction of time the system is up and running. Power consumption or performance per watt, etc. Second, time has many components, but computer architects usually focus on CPU time, which is the time the CPU is computing, not the time waiting for I/O or running other programs. Third, SPEC, which stands for Standard Performance Evaluation Corporation, is a successful benchmark suite for desktop computers. Not quite as successful, but still often used for embedded computers, is the so-called EMBASY, which stands for EDN Embedded Microprocessor Benchmark Consortium. Fourth, you shall not use the arithmetic mean to average the normalized execution time, because it can lead to different results depending on the reference machine. Use the geometric mean instead, which is summarized here for your convenience. I continue with the summary of these lessons on performance. Fifth, Amdahl's law, which is given by this equation here, is an important equation in computer architecture, perhaps even the only law we have. Amdahl's law directly implies the design rules make the common case fast. Six, there are not many equations I want you to memorize. Remember, computer architecture is not rocket science. But here's one that is based on common sense. The execution time of a program is given by the number of instructions executed times the cycle per instructions, or CPI, times the cycle time, or equivalently divided by the clock frequency. This equation immediately shows that the performance can be improved by reducing the number of instructions, or reducing the CPI, or increasing the clock frequencies. Furthermore, the performance depends equally on these factors. Seventh, our lucky number. And finally, 3 important rules of thumb to make processes faster are exploit parallelism, exploit locality, and make the common case fast. Finally, some test yourself questions. I will not provide the answers to these questions. You have been given all the information you need to answer them. This concludes this video. Hope to see you back.